Hello and welcome to the lecture on spherical coordinate system. In this lecture, let us try to understand spherical coordinates and how we use them. So, um, I have drawn here a small volume element of a sphere. So, basically, the sphere is like this, and when we map these Cartesian coordinates with the spherical coordinates, then we can understand how to use the spherical coordinates. So here I have taken small volume element. I am just drawing this here, the same small volume element. See, this is curved, but it appears linearly because it is a small volume element. Basically, when we consider differential element of a curve, so for example, if we take a curve and we consider only small differential length, this will be linear. It is linear in nature. So that's why even though it is curved, this small section, see, you can see the curve like this. Here also it is curved. Similarly, this is also curved. So this is a section, um, a small section of the sphere. Like, for example, if you take a cricket, like a tennis ball. So for example, the tennis ball inside it is hollow, and imagine that the tennis ball thickness is uh, very little. Consider that it is only differential element, just for understanding sake. It is not that the tennis ball thickness is not that less, but just for our understanding sake, imagine that it is very thin compared to that, and in the order of dr. So here dr is the thickness of dr is the thickness of that tennis ball. So now when we see here, this is the thickness. So it is actually dr. um, and now we have in this direction as well as, so the small volume element is like a cuboid. It has three sides. So one side is dr, this side. Now we will find this side what it will be, and this side also we will find. So before that, I want to define the coordinates. So in spherical coordinate system, we the coordinates are and theta. So here r is the radial distance. Basically, this radial distance, it is calculated from origin to the point P. Uh, it is the distance. So the magnitude of this r, whichever we write in here, that is equal to the distance between origin in the Cartesian coordinates when we map between origin and point P. Point P, whichever we consider. So for example, we can consider point P here. So this will be the r, and phi is the azimuthal angle, and theta is polar angle. So phi is the, if we take xy plane. Now what we are doing is, so how we are going to calculate the phi. So for this point, let's get the coordinates. So I am just naming this point. Let me name this point as So this point, let me give a name, say that it is point P. So let's write the coordinates. In order to write the coordinates here, we measure the distance from this point to origin, that is r, a variable. And next is azimuthal angle. In order to calculate the azimuthal angle, we have to see this from this r, we have to come along this curve to xy plane such that where z equal to 0. So now this point, the same point, when we are um, projecting onto the xy plane where z equal to 0. So the basically what does that mean? That means that suppose P is at a distance r. So please remember that r is not the radius of any sphere here. R is just the distance from origin to the point P. So please keep in mind that r is not a radius here. It is just the radial distance, that is from origin to point P, whichever we are considering in the spherical coordinate system. So I'm considering P here. Now um, so where that r is coming on the xy plane, if we um, so if we draw from here like the same curve, uh, like if we draw a circle with center origin, if we keep drawing a circle. Okay, let me use some other color. uh, so let me use this green color. Now let me draw a circle. So I am drawing this circle such that origin is the center. So for this circle, origin is center, and for this circle we have drawn such that it is passing through the point P. So r is the radius. Just for this circle, r is radius. Now this circle, it is passing through the xy plane. So it is passing through the xy plane. Now when this point reaches a place where z equal to 0, so here uh, we are projected like this. So the point comes here. See, on the circle it came exactly in the xy plane. So at this point z equal to 0. So this point lies in um, point lies 0 plane. Okay, so it lies in z equal to 0 plane. Now at that instant, for this line, we measure from x-axis in anti-clockwise direction. So angle measured in anti-clockwise direction with respect to a positive x-axis. See, the words might be so many in describing that, but it is very simple conceptually. You can understand easily what I am talking here. So now we know that this is phi. So we have taken differential length element here. So this will be d phi. Okay. Now here similarly polar angle. Uh, so I am writing what is polar angle. Now we got here phi. The other is the polar angle theta. So polar angle theta, let me use another color. So let me write what is theta. Theta is the angle between z-axis and the line joining origin and point P. Here the line joining, this is the origin O and point P, this line. Z axis is this. So this angle is theta. Now this angle is theta, and for this differential um, element or differential length here, small length in this, we have d theta. Now also we have unit vectors here for the uh, spherical coordinates. Let me write the unit vector. So r cap, it is along the direction, um, along the radial direction. So what is radial direction? That is along line joining O and P, O and point P. So that is the unit vector r cap direction. Now what is the phi cap direction? So let me name this point as it is z equal to 0. So let me, in the, it exists in z equal to 0 plane. So let me write this as r, point r. Now so I have to talk about the unit vector for the azimuthal angle coordinate, which is phi cap. Now its direction is, so direction of the tangent at r, and you know what is r, as I have explained how we got to the r. So what, wherever may be the point p in the space of the sphere, um, just draw the circle, keeping the draw the circle such that circumference pass through the point P and O is the center. So now wherever we get z equal to 0, wherever the circle goes through z equal to 0 plane, such that we get a point R, um, so that will be uh, so that will means direction of the tangent is at that point. Or so let me draw that. um, I can also draw um, x, y and z plane. Now so that circle I'm just plotting here. Now we got that point R here. So when we draw like this, we get 5. So the direction of the unit vector phi cap will be, so it will be like this. So this is the phi cap direction. So when we take this up, it will be like in this. Let me plot here. Also, I will plot. Um, so r cap direction is going in this direction, and we have phi cap in this direction. I apologize. I had a confusion that these two should be interchangeable. So the second one will be the polar angle. I apologize for that. Let me correct my mistake. So so second will be theta. So theta will be this, and 5 is the third coordinate. Here also please change. theta, then phi. So phi is the azimuthal angle and theta is the polar angle. We have dr. So we are talking about unit vectors. So phi cap is the direction of the tangent at r, and theta cap. So now see in this, let me draw here. So the point P exists at this point. So this is the actual point. But to calculate phi, we have taken the circle and just find phi cap here. So in parallel to this, so this is phi cap, which is parallel to the same thing which I mentioned here. Now r cap, if we see, r cap is along the this direction. So it will be like, so this is r cap, and now we have theta cap, which is perpendicular to both r cap and phi cap. So this is a theta cap. These are the three unit vectors. So perpendicular to both r cap and phi cap. Please note that in spherical coordinates, this is the order: first radial distance, then polar angle, and at last azimuthal angle. So I want to represent this differential volume element here. I almost try to show it as linear, something as linear as possible. Let me have the eraser. Um, so the small volume element, consider, actually it will be very linear when we take the small sort of thing. So these are the two layers uh, that are there, but we have to draw the in 3D. Let me use another color. So each dimension I will draw with one different color. So here let me use sky blue for another side. So here we have seen the, now you can understand that these two are the layers, like in a tennis ball. This is the inner layer and this is the outer layer. So the normal to this inner layer and outer layer is the radial distance. Hence, this red dotted color. Let me change immediately. So this side it is dr, the small differential length element along the radial distance, along the r cap direction. And now we have to determine this green color part and blue, sky blue. So imagine that this dr is same for these red lines. Let me draw somewhat thick, and this one, these are all equal. Now let's see the green part. So here this is the green part, and um, the point P is at a distance r. We have this is at r and this is also at r, because it is along a if we can consider a circle passing through this. So it's like it is at r and it is also at r, making an angle between them d theta. So the arc length will be length times the angle. So that's why this length will be r d theta. Radius times radius times the angle. So here radius is nothing but radial distance when we consider this circle. Now we have to determine the sky blue part. So let me. So that is this side how much. Now in order to find that, observe here. So this one, it is like it is going like this and forming a. Suppose when you take the earth, you will observe the latitudes and longitudes. So here this this side, whichever we have mentioned here in sky blue, it is forming a circle like latitude on the sphere. So it is basically the small section which we are taking here is nothing but a small length on the latitude. So this is what we need to find for this. Now to find that, we need to know the. So this latitude is like a circle. It is a circle. Um, Now we have to determine what is the radius of this circle. To do that, we have to draw a triangle like this. So we have our point P. This is origin, by the way, and this is point P. See, from point P we are taking a little bit differential length to calculate our and this point P, what we let's call this as Q, where Q is the center of this circle. How it is looking here, we have tilted a bit, but the thing is, it looks like this. This is P, this is Q, and we have origin and theta. So OQ is along Z axis. We have to find PQ, and we know OP is equal to R. So sine theta is equal to um, opposite side PQ by this hypotenuse OP. So here from this you can calculate PQ. So PQ will be, sorry, so which gives rise PQ is equal to R sine theta. Now R sine theta is the radius of latitude. So radius of latitude is how much? R sine theta. Okay. So what is the arc length of the this small section? The arc length of this small section would be radius times the angle it is making, and we know that angle it is making is d phi here. So this angle is also d phi times r sine theta. So that will be, this length will be r sine theta. So now let's so it is, all these are equal linear because we are considering differential element. So let's draw as a perfect cuboid now. Perfect cuboid with sides in this fashion. So just following the same thing, like this is dr and this is r sine theta, sorry, d theta, uh, r sine theta d phi, sorry, let me, okay, r sine theta d phi, I forgot to write d phi because it is the angle making is d phi here. So we have to multiply r sine theta d phi radius into the angle it is making, that will give the arc length. And we know that this is r sine theta d phi, and this side we get r d theta. So which is straightforward because d theta, and we have already calculated this. So now it is a perfect cuboid. So it is a differential volume. Differential volume dV is equal to so let's multiply dr times r d theta. So multiplied with r sin theta d phi. Now we get dV is equal to r square. Sorry, here sin theta r square sin theta d theta d phi, and also dr. So just interchangeably. Now, so now when we do volume integration by applying the all the limits dV, we will get volume of sphere. Sorry, I forgot to tell one thing in this, that is the range of these coordinates. So let me write here the range of coordinates. We have r, theta, and phi. So r ranges from 0 less than or equal to r less than infinity, and theta polar angle, if you see here with respect to z axis, you can measure all the way up to this point. So it is basically from 0 to pi. That is the range of this. So 0 less than or equal to theta less than or equal to pi, and azimuthal angle, like what we have seen. What is the definition for azimuthal angle? Um, Maybe I have so angle measured in anti-clockwise direction with respect to x-axis. So this phi I have written angle measured in anti-clockwise direction with respect to positive x-axis. So with respect to positive axis, if we start here, we start from 0, and as we go along in anti-clockwise direction, we will end up to 2 pi. So 0 less than or equal to phi less than or equal to 2 pi. But that is not the case in polar angle, because in polar angle theta we have written somewhere. I don't know. Theta is the angle between z axis and the line joining origin and point P. So this will be in the range of 0 to pi itself. Now, in order to get the volume of sphere, we have to apply all the limits here. All the limits based on whichever is applicable. So, for a sphere of radius r, for a sphere of radius r, it will be from 0 to so let's take capital R, because small r we are continuous, we are always using small r. So let's consider capital R. Now for capital R, so we have to do from 0 to capital R, because we have the differential element, we have to consider from 0 to the surface where r exists. But theta and phi we have complete, incomplete, that is 0 to pi, sorry, and 0 to 2 pi. Now let's apply those things. 0 to r, 0 to pi, 0 to 2 pi, and differential element dv is r square sine theta, r square sine theta dr d theta d phi. Now we have to integrate this each one. So when we do r square dr, so basically this is triple integral. It will be like this: 0 to r square and dr. These are the variables in this, multiplied by 0 to pi, and corresponding one is d theta because that's the limit, and the other one is 0 to 2 pi d phi. Oh, sorry, here sine theta will be there. I forgot to put sine theta. Let me just go back. So 0 to pi, and here we have sine theta d theta, and 2 to pi, it is just d phi. Now when we do integration, we get r cube by 3, and the limits are from 0 to r, multiplied with sine theta. When we integrate, we get minus cos theta. It is from 0 to pi, and we get d phi. When we do, we get phi, which is 0 to 2 pi. Now by applying this r cube by 3, so for this we have minus cos theta, so I'm just taking minus 1 outside, then calculating here cos pi, which is minus 1, minus cos 0 is again 1, and phi is 2 pi minus 0. Now it is like 2 pi minus 1 is minus 2 into minus 1 is 2, 2 times 2 pi is 4 pi, r cube by 3. So this is the volume of sphere with radius r. Volume of Similarly we can okay, this is a differential volume element. Now let's see the differential surface. ds is the differential surface. So now when we take sphere, we have along r cap direction the surface area. Also we can consider other directions as well, depending on what we consider. For example, in radial direction, when r cap is the normal, it will be so along r cap direction, so dr, this is the r cap direction. Along the direction, the surface area will be r sin theta d phi times r d theta. Or else let me draw the cuboid again, just to avoid confusion. Please imagine the drawing, I mean perfectly. Your visualization should be perfect. Don't mind about drawing. So this is the r cap normal direction. When r cap is normal, we have sides r sin theta d phi, and this is the r d theta. So here ds will be r square sin theta d theta d phi, r cap. See, surface element is a vector, differential surface is vector, and differential length is also a vector, but not the differential volume. So this is a differential surface along r cap direction. Now let's see along phi cap and theta cap. See, we have r d theta and r sin theta. Now when we consider along theta cap, it will be r square sin theta. um, we are considering along theta cap, so it will be dr and d phi. So exactly that's it is. Now along phi cap, so we are considering along phi cap, so dr d theta phi cap. So based on which side we are considering, but predominantly maybe towards radial direction the surface might be important for most cases, but let's not forget that this is not useful. This is also useful, other two surfaces as well. Now we can calculate the surface area of the sphere. Surface area of sphere with r, with radius r. So in order to do that, see, surface area we can calculate when the normal direction is r cap. So we have to consider this surface for that. And for surface integral, we have double integral. Surface element, I am just writing r square sin theta d theta d phi. And we know the value of r directly, which is radius. It is constant because we are considering the surface which is at a distance r from the center, so r square. Now limits we will apply d theta as 0 to pi and 0 to 2 pi. For this, let's take r square outside, which is constant, and sin theta is minus cos theta. We can take minus outside. 0 to pi, and then d phi is phi, 0 to 2 pi. So we have already calculated cos theta. From pi to 0 it is minus 2. Minus 2 of minus 2 is 2. So it will be 2r square. Now it is 2 pi. So we get 4 pi r square. See, these are very, this is how we calculate, but these are very very straightforward or easy, like, because we are considering everything. But we can also calculate many, whatever the structure it is given. For example, in problems in the exam, they might give like this. Suppose if a sphere is given like this and this section is hollow, then what is the effect due to this? Then at that time it is very important. At that time these coordinates will be very important, like what, from where to where we can consider. Sometimes you also can consider the symmetry, etc. But if you are familiar with the coordinates, you can apply the limits properly. So this is how spherical coordinates are important. You just have to practice more problems and see how to apply the coordinates, then it will be easier. So please practice more problems. I will also come up with standard questions of NAT, that is numerical answer type, and multiple choice questions, as well as multiple select questions, similar to GATE standard, and same type of questions. So thank you so much for watching this video. If you like this video, please give a thumbs up, and please subscribe. You will get more videos on EMT. Thank you.